The 2020s will see the launch of the James Webb and the Nancy Grace Roman Space Telescopes. These are NASA's next two flagship astronomy missions and are often considered successors to the Hubble Space Telescope. But Hubble is an optical telescope, while Webb and Roman we'll see in the near and mid-infrared. In that regard, Webb and Roman are more accurately described as successors to the recently retired Spitzer Infrared Space Telescope. Meanwhile, Hubble has been in service for over 30 years, and the Chandra X-Ray Observatory has been up for 21 years. Both are working well, but they're showing their age. And while the Webb and Roman space telescopes are certainly the flagship missions of the 2020s, astronomers are already planning the next 4 new great observatories for the 2030s and beyond. Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. And today we're taking a look at 4 future space telescope proposals that, if selected, will have the same transformative effect on astronomy as the original great observatories had in the 1990s and 2000s. And it might seem a little strange to even be talking about the next generation of space telescopes when the James Webb Space Telescope is a decade behind schedule, has blown way past its original budget, and it hasn't even launched yet. But large-scale projects take well more than a decade to go from concept to first light, even under the best of circumstances. And that's why the National Academy of Sciences brings together the astronomical community to produce the Decadal Survey on Astronomy and Astrophysics. The Decadal Survey sets the priorities in astrophysics for the next decade, but it's more than just a glorified wish list. Congress makes budgeting decisions based on them. Missions like Chandra, Spitzer, James Webb, and Roman were all given top priorities in previous decadal surveys. Having telescopes in space frees us from the distorting effects of Earth's atmosphere, but it also opens up the entire electromagnetic spectrum for astronomical observations. But putting a telescope in space means fitting it into a launch vehicle first, so every design requires trade-offs between the mission's science goals, the launch vehicle capabilities, and the technology required to make it happen. Oh yeah, and also costs. To that end, the 4 study groups produced final reports on 4 space-based astrophysics missions for the 2020 Decadal Survey. All 4 missions will operate at the Sun-Earth L2 point. This is like a gravitational balance point between the Sun and Earth. It allows a telescope to block out the Earth, Moon, and Sun with a single sunshade. This keeps the telescope cold and dark, yet still keeps it relatively close to allow it to be serviced robotically. Together, these 4 missions could become the new great observatories of the 2030s. So let's take a look and see what they came up with. Number 1, the Habitable Exoplanet Observatory, or HabEx. HabEx's primary mission is to directly image and characterize Earth-like exoplanets for the first time. Thanks to the Kepler mission, we now know that virtually all stars host at least one planet, and as many as 20% of those planets may be Earth-like. But of the 6,000 exoplanets detected so far, only a handful have been directly imaged. Planets are lost in the glare of the star, so the only way to see them is to block out the star's light with a tiny disk called a coronagraph. The current state of the art looks something like this. Here we see 4 giant planets making their way around the star HR 8799. All 4 of these planets are larger than Jupiter, and the one just outside of the coronagraph is farther away from its star than Saturn is from the Sun. But an Earth-like planet is smaller and orbits much closer to its star than the planet shown here. Such a planet would reflect just 1/10,000,000,000th of the light of its parent star. That's why HabEx will use not 1, but 2 spacecraft to image exoplanets. The first is an optical telescope with a built-in coronagraph. The second is a 52-meter diameter starshade that blocks the star. The telescope itself has a 4-meter diameter mirror which collects more than 10 times the amount of light as Hubble. But even in space, there's no such thing as a perfect focus because there's no such thing as a perfect mirror. Starlight entering the coronagraph gets distorted by the tiniest of imperfections in the telescope's mirrors. Without the coronagraph activated, these distortions spread the starlight into a series of concentric rings, with most of the light blurred into a tiny disk at the very center. This is an effect called diffraction. The coronagraph uses a mask that's specially designed to block most of the starlight and redirect most of the light it doesn't block off to the edges of the beam. Next, a washer-shaped disk blocks the light at the edges of the beam. This removes the rings, leaving behind only trace amounts of starlight. With most of the starlight removed, it's now possible to image the planet. Since the planet is located next to the star, light from the planet arrives at an angle, misses the mask, and passes through the washer. As more light is collected, blobs of leftover starlight obscure the planet. Remember, these blobs are due to light diffracting off the imperfections of the mirror. A deformable mirror cancels out those distortions and allows the faint light from the surrounding planets to come into view. When the light from these two planets are passed through a spectrometer, it becomes possible to see which gases are present in the planet's atmospheres. But the coronagraph is only half of HabEx's exoplanet superpowers. The starshade blocks starlight by positioning itself between the telescope and the star. If the starshade were a simple disk, starlight would just diffract around it. Instead, starlight uses specially designed petals to eliminate most of the diffraction and let the planets come into view. Earlier concepts launched starshade together with the HabEx telescope, but the current proposal calls for each spacecraft to be launched separately. However, getting a 52-meter disk into space means folding the starshade up origami style and unfolding it once jettisoned from the booster. Once they arrive at the Sun-Earth L2 point, starshade and HabEx will maintain a separation of approximately 76,000 kilometers. That's about 6 Earth diameters apart. HabEx's starshade and its internal coronagraph are designed to complement each other, each providing capabilities the other cannot. The coronagraph is ideal for detecting exo-Earths and determining exoplanet orbits, while the starshade is optimized for wide-field mapping of the planetary systems and optimizing observations for spectral analysis. Although a starshade has yet to fly, a lot of work has been done over the last decade to develop and demonstrate the technology. Smaller mock-ups have shown that starshade can unfold itself and deploy its petals reliably. The two spacecraft would have to maintain precise alignment during observation. This would be accomplished with a two-way radio and laser communication to share position data between the two spacecraft. Automated systems would make precise microthruster adjustments to maintain alignment. Precision formation flying has already been demonstrated on a smaller scale on previous missions, such as NASA's Gravity Recovery and Climate Experiment Follow-on mission. GRACE-FO, as it's called, uses two spacecraft to measure minute changes in the local gravitational field of Earth, often due to ice loss and sea level rises. The two spacecraft use a laser link to share position data, and onboard algorithms make real-time attitude adjustments. However, changing targets means the starshade would have to move to position itself in front of another star. And that could take starshade approximately 2 weeks to complete that maneuver. In the meantime, the HabEx telescope would still carry on science observations as a general-purpose observatory that's sensitive to ultraviolet, visible, and near-infrared wavelengths. Both HabEx and starshade rely on thrusters for positioning and station keeping. However, they could both be refueled and serviced robotically. Servicing missions could also include upgrading instruments, replacing microthrusters, avionics, and power systems. HabEx is designed to be a great observatory, but one that manages risk. And that's why the telescope uses a 4-meter monolithic mirror as opposed to a segmented design that would have to be unfolded like on James Webb. That makes the spacecraft just large enough to fit into the SLS Block 1B's 8.4-meter fairing. Starshade could be folded up into a 5-meter fairing and be launched using the Falcon Heavy in expendable mode, although SpaceX's Starship would probably be a better option for both spacecraft. Number 2. The Lynx X-Ray Observatory. Of the 4 proposed missions, Lynx is the only one designed to probe the universe at high energies. It's also the only one whose name is not an acronym. According to myth, the Lynx was believed to be able to see through objects and reveal their true nature. That's a perfect name for an X-ray telescope. Bringing X-rays to a focus requires a very different approach than with other forms of light. X-rays would pass straight through an ordinary mirror, but if X-rays strike a mirror at a shallow angle, they will deflect off the mirror like a stone skipping off water. X-ray telescopes like NASA's Chandra and ESA's XMM Newton take advantage of this effect by arranging mirrors in a series of concentric shells. But Lynx will take this approach to a much higher level. Whereas Chandra uses 4 shells of grazing incidence mirrors, Lynx will use 12 metashells of densely packed thin mirrors made up of multiple smaller modules. This makes Lynx 100 times more sensitive than Chandra. That will allow Lynx to image the very faint X-ray sources that are well below Chandra's detection limit. Lynx will detect the high-energy radiation coming from protostars deep inside their stellar cocoons. Astronomers will then be able to understand how this high-energy radiation affects the growth and formation of their planetary systems. Lynx will also be able to study the formation of the first black holes and galaxies in the early universe and trace their evolution over time. In fact, understanding how black holes grow and evolve over time is one of the key unanswered questions in astrophysics. But doing so requires surveying the early universe for the X-ray signatures of intermediate mass black holes as they feed on their surroundings. Lynx's sensitivity will allow it to work much faster while probing far deeper into the X-ray universe than any previous mission. A single 100,000 second exposure with its high-definition X-ray imager will see deeper than the 7 million second Chandra Deep Field. This detailed image of Kepler's supernova required nearly 9 days of Chandra's observing time. Lynx will create an even more detailed image over a wider field of view in just a few hours. Lynx is designed to be built and launched sooner rather than later. The spacecraft uses a lot of Chandra's design heritage and has similar dimensions. That allows it to fit into the standard 5-meter fairing of heavy launch vehicles such as the Delta IV Heavy or Falcon Heavy. By the way, those are vehicles that are not on the drawing board. They are available today. Lynx is designed to operate for 20 years, but it's also designed to be robotically serviceable as well, which could easily extend its lifetime. As proposed, Lynx would have a 100-fold increase in sensitivity, 16 times the field of view, 800 times the survey speed, and 10 to 20 times the spectral resolution. Lynx isn't incremental, it's transformational. Number 3, the Origins Space Telescope. As its name implies, Origins is designed to trace our cosmic history, from the formation of the first galaxies to the creation of habitable worlds. To do that, Origins employs a 5.9-meter infrared telescope. That makes Origins 1,000 times more sensitive than NASA's Spitzer's and ESA's Herschel space telescopes. Origins will be much larger than its predecessor, though not quite as large as the 6.5-meter James Webb Space Telescope. But its design was chosen to be much easier to build and deploy than James Webb, which makes it less likely to go over budget. Infrared telescopes have to be kept extremely cold in order to detect the faint heat signatures coming from the universe. This is usually done with a combination of sunshades and cryocoolers. But this can make the overall spacecraft bulky. James Webb will be the largest space observatory ever flown, but it was designed to be launched by the Ariane 5 launch vehicle, which has a 5.4-meter diameter fairing. That's why James Webb has to be folded up origami style and then unfold itself once in space. But that's also why James Webb is so far over budget and behind schedule. Ensuring the observatory can withstand the rigors of launch and still deploy itself has blown up James Webb's budget at the expense of other astrophysics missions. When James Webb was designed, the Ariane 5 had the largest launch fairing available. It's even wider than the Space Shuttle's main cargo bay. But with the Space Launch System, SpaceX's Starship, and Blue Origin's New Glenn in development, it's looking like it'll be possible to launch large telescopes that won't need to be unfolded once in space. To that end, the Origins study team opted to go with a much larger version of the Spitzer telescope, which is much easier to build. Origins is 6.3 meters in diameter in the launch configuration. That allows it to fit in the SLS and Starship launch vehicles. Once on orbit, Origins only has to deploy its communication antenna, solar array, telescope cover, and sunshields. Speaking of which, JWST uses a 5-layer sunshield to keep the telescope passively cooled, while Origins uses a 2-layer sunshield plus a radiator. Like Spitzer, Origins will be surrounded by a barrel, which is highly reflective on one side toward the sunshield and painted flat black on the other side facing into deep space. This turns the bottom half of the telescope barrel into a radiator, cooling the barrel down to 35 Kelvin. Origins also uses an advanced cryo-cooling system to bring the temperatures down to 4.5 Kelvin. By contrast, Spitzer was cooled to 5 Kelvin. Half a Kelvin might not seem like much, but it represents a huge leap in sensitivity. Remember, the cooler the telescope, the more sensitive it is to heat, so every fraction of a degree counts. Origin's cryocoolers are designed to last at least 10 years, but the spacecraft is designed to allow its coolant and propellant to be replenished and its flight hardware instruments to be replaced and upgraded anytime. A single monolithic mirror will always collect more light per square meter than one made from hexagons, but building a single 5.9 meter mirror that can withstand the stresses of launch is a risky proposition. So the proposal currently calls for a segmented mirror made from two sets of wedges rather than hexagons. This allows the mirror to maximize the light collecting area that can be squeezed into the launch fairing. Once on orbit, tip-tilt actuators behind each mirror segment brings the light to a focus. Once settled into its orbit around the Sun-Earth L2 point, Origins will be able to begin tackling the questions it's designed to address. With deep spectroscopic surveys, Origins will build up a 3D map of the universe. This will allow Origins to trace galaxies and their supermassive black holes as they evolve and grow over cosmic time. For example, this is an image of a pair of two colliding spiral galaxies taken with the Hubble Space Telescope in visible light. The collision set off several bursts of star formation, which are still surrounded in their dusty cocoons. These cocoons lie somewhere between the merging nuclei. At mid-infrared wavelengths, Spitzer is able to detect emission from the dust, but cannot precisely map its location. But at more than 100 times Spitzer's sensitivity and 10 times the resolution, Origins is able to precisely map the location of the dust clouds in a single 1-second exposure. This allows Origins to address questions of how and when do planetary systems form around their stars. What role does water play in the formation of habitable planets? How were water and life's ingredients delivered to Earth and to exoplanets? And can life find a way to survive on planets around red dwarf stars? Origins is set up to be the infrared flagship mission to follow the James Webb and Nancy Roman infrared observatories. But if its design seems a little too conservative for your tastes, take a look at this. Number 4. The Large Ultraviolet Optical and Infrared Surveyor, or LUVOIR. If the other designs steer clear of JWST's origami approach, LUVOIR embraces it to deliver the largest telescope ever conceived. At up to a whopping 15 meters, such an approach is the only way we know of to deliver such a large telescope into space. But how large the telescope can be ultimately depends on the availability of future launch vehicles. That's why the LUVOIR study team considers two possible architectures. Both architectures employ a large sunshade to keep sunlight out of the telescope and help keep the payload from overheating. The sunshade is similar in some ways to the one developed for JWST, but LUVOIR doesn't have the strict cooling requirements, so its sunshade is considerably simpler. JWST is an infrared telescope, so its sunshade has to keep the telescope as cold as possible. This requires 5 layers that must be precisely aligned and spaced apart from each other using fine positioning mechanisms. LUVOIR is a UV optical and near-infrared telescope, so its thermal requirements are much easier to meet. Instead of JWST's 5 layers, LUVOIR uses just 3. And these layers don't have to be as precisely aligned, so there's no need for fine positioning mechanisms. As a result, the sunshade can be stowed and deployed much more simply. However, LUVOIR may need to point into the sunward hemisphere from time to time, and that's why it uses a much larger sunshade to keep the telescope in shadow whenever it needs to point inward. The LUVOIR study team's mandate was to consider designs for a UV optical and near-infrared telescope in the 8 to 16 meter range. LUVOIR-A proposes a 15-meter segmented mirror with 4 instrument bays. This makes it just large enough to fit into the SLS Block 2 launch vehicle. However, Block 2 represents the 3rd generation of SLS, and Block 1 has yet to fly. That's why the LUVOIR-B design uses an 8-meter mirror with 3 instrument bays. Ideally, it would be launched on an SLS Block 1B, a SpaceX Starship, or Blue Origin's New Glenn, but it can also fit into an industry-standard 5-meter fairing as well. And this makes the LUVOIR-B design much more flexible, though at the cost of a smaller aperture and 1 less science instrument. LUVOIR is designed for coronagraph observations of exo-Earths, much like HabEx, but coronagraphs perform better when the primary mirror is unobscured. That's why LUVOIR-B uses an off-axis design. But such a design also requires the secondary mirror to be extended farther away from the primary than in the classic on-axis configuration. LUVOIR-A's 15-meter design requires a off-axis secondary to be at a length that cannot fit inside of a launch fairing. So the traditional on-axis approach was chosen for LUVOIR-A, but the central obscuration was kept as small as possible. Both architectures keep the sunshade facing the sun while the telescope is free to point in any direction on the leeward side. Over the course of a year, LUVOIR would be able to view the entire sky in all directions. However, the entire observatory could be tilted by as much as 45 degrees inward toward the sun to make observations of Venus, comets, transiting exoplanets, and targets of opportunities, all while keeping the observatory payload in shadow. Now, extending the sunshade, deploying the secondary, and unfolding the mirrors gives me a case of the screaming heebie-jeebies. But for better or for worse, those technologies have finally been tested and integrated into JWST. Because LUVOIR doesn't have the same thermal requirements as James Webb, it is in some ways a much simpler design. JWST is supposed to launch in 2021. If it successfully deploys, it will make LUVOIR much more viable. But unlike JWST, LUVOIR is serviceable and upgradable thanks to its modular design. It will carry 10 years worth of consumables that can be replenished. Non-serviceable components are designed to last at least 25 years. Both designs are larger than anything ever flown or proposed, but what is the real advantage of a 15-meter design over an 8-meter design? Well, one of the key science goals of LUVOIR is to search for habitable planets and characterize their atmospheres. But an Earth-like planet is 10 billion times fainter than its host star. That makes exo-Earths among the faintest objects we've ever detected. Seeing them requires collecting as much light as possible. A telescope's light-gathering power goes as the square of its aperture. A 2-meter telescope can collect 4 times the light of a 1-meter telescope. A 3-meter telescope can collect 9 times the light, and so on. So how do the proposed optical designs for LUVOIR compare? Well, the Hubble Space Telescope's primary mirror is 2.4 meters. HabEx's 4-meter mirror gathers nearly 3 times more light. At 8 meters, LUVOIR-B gathers 11 times the amount of light, and LUVOIR-A's 15-meter gathers more than 30 times more light than Hubble. In fact, the 15-meter design is a 14-fold increase over HabEx and a 3.5-fold increase over LUVOIR-B. Okay, so it collects more light. Well, so what? Well, one of LUVOIR's science goals is to find out how common Earth-like exoplanets are. And that means surveying as many systems as possible to build up reliable statistics. LUVOIR-B's 8-meter design is expected to yield somewhere around 28 habitable candidate planets. That's just enough to achieve statistical significance. However, LUVOIR-A's design is expected to yield around 54 exo-Earths. That exceeds the minimum statistical requirement and provides a margin against uncertainties. It would effectively answer the question of, are we alone? The larger design also means data can be collected faster, requiring less time needed to observe a planet. Shorter exposures would allow us to get a better idea of the distribution of continents and oceans on these planets. The exoplanet case is just one of LUVOIR's science goals. It would be able to investigate the formation of stars, the planetary systems, the earliest galaxies, and the acceleration of the universe's expansion in unprecedented detail. But you already know that. LUVOIR would be a true successor to the Hubble Space Telescope. But if LUVOIR is going to become a reality, the next generation launch vehicles are needed to get them into space. The LUVOIR-B design could be launched on the SLS Block 1, Block 1B, SpaceX Starship, and on Blue Origin's New Glenn. LUVOIR-A could be launched on SLS Block 1B with improved engines, and on Starship with a modified fairing. To that end, the LUVOIR study team consulted with SpaceX, and SpaceX found that a modification to the Starship fairing to accommodate LUVOIR-A is certainly feasible. So, which of these concepts are you most excited about? I'm personally leaning toward all of them. Each of these telescopes brings unique capabilities the others cannot. and they'll complement the next generation of ground-based telescopes like the Vera Rubin Survey Telescope, the Giant Magellan Telescope, the 30-meter telescope, and the Extremely Large Telescope. These observatories will not only allow us to answer the questions we have today, but they'll allow us to investigate questions we haven't yet thought to ask. By the way, most of these giant ground-based telescopes are under construction right now. I made some videos about them, so make sure you check them out when we're done here. Thanks once again to my patrons for supporting this channel, especially to Michael Dowling for his cosmological level sponsorship. If you'd like to support Launchpad Astronomy for the price of a cup of coffee every month, please check out my Patreon page. And if you'd like to join me on this journey through this incredible universe of ours, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay home, stay healthy, and stay curious, my friends.